Welcome to the deep dive. Today we're tackling Chainlink Data Streams. Think of it like plugging your smart contracts directly into the real world to get live information.
Exactly. And in this deep dive, we're not just waving our hands at the idea. We're going to get into the nitty-gritty of how you actually pull that data in, make sure it's legit, and then store it.
Right.
Our focus today is a classic example, getting the price of ETH against the US dollar into a smart contract.
And to guide us, we've got some fantastic material, excerpts from the official Chainlink documentation, specifically their Getting Started with Chainlink Data Streams remix guide.
Yep, that's the one.
So our mission today is to kind of cut through the technical fog and make this clear for anyone who's curious about how this stuff really works. Okay, so before we even think about touching any code, what are the foundational things we need in place?
Well, the documentation lays out a few key starting points. First, you'll need access to a blockchain network, either the main Ethereum network or a test network for experimentation. Typically, you'd request access to these. Then, a good grasp of smart contract basics is crucial. We're talking about being comfortable with Solidity, having a MetaMask wallet, and knowing your way around Remix.
Right, the essential toolkit for building on Ethereum. And it sounds like we'll be working on a specific test network for this demonstration.
That's right. Yeah, the guide focuses on the Arbitrum Sepolia testnet. You'll need a bit of test ETH to cover the transaction costs, what we call gas, and some test ILink tokens on Arbitrum Sepolia. Think of testnet tokens as like play money for developers.
Okay, play money.
Since we don't want to spend real ETH and Link while experimenting, these faucets generously drip feed us these test tokens so we can pay for transactions and interact. The docs point you to these faucets.
Faucets, got it. And the guide also mentions needing to fund contracts with Link. Why is Link involved here?
Well, ILink is the fuel that powers many Chainlink services. In this particular setup, the smart contract will be working with the upkeep contract. It actually takes on the responsibility of paying for the on-chain verification of the data.
It does this using Link, so having some Link available to this contract is, what allows it to function correctly.
Yeah. All right. With our virtual sandboxes ready, the first concrete step is deploying a Chainlink Automation upkeep contract. What's the job of this automated keeper?
Think of the upkeep contract as your autonomous data retrieval agent. Its purpose is to automatically fetch data from the data stream we specify whenever certain conditions are met.
Like a trigger.
Exactly. In our case, it will be triggered by a specific kind of event log.
And the particular data stream we're interested in is the ETH price feed on the Arbitrum Sepolia testnet. The documentation even gives us its unique identifier. Wow, 0x0003, ending in base 782. Quite a mouthful.
It is, yeah. And as the documentation notes, if you're curious about fetching prices for other cryptocurrencies, their Data Streams Crypto Streams page has a whole catalog of available stream IDs.
Okay, good to know. So how do we actually get this upkeep contract onto the Arbitrum Sepolia network using Remix? Right, so the guide walks us through it step by step. First, in the Remix IDE, you open the streamsupkeep.solvable contract and compile it. You might see some warnings pop up, but for this example, the documentation says we can safely ignore those.
Okay, ignore the warnings.
Next, you need to make sure your MetaMask wallet is connected to the Arbitrum Sepolia network.
Right.
If it's a new network for you, the documentation mentions you can find all the necessary details like the chain ID and the ILink token contract address on their link token contrast page.
Got it. Network connection confirmed. What's the next move in Remix?
Okay, so on the Deploy and Run Transactions tab in Remix, you need to select Injected Provider MetaMask as the environment. This tells Remix to use your connected MetaMask wallet.
Makes sense.
Then, in the contract section, make sure the Streams Upkeep contract is selected. And here's where we plug in a crucial piece of the puzzle. You need to provide the address of the Arbitrum Sepolia verifier proxy.
The verifier proxy.
Yeah, for this testnet, it's 0x2F0 ending in 488A. The documentation points out that you can find these verifier proxy addresses on their stream addresses page.
So this verifier proxy sounds important. We'll definitely want to understand its role better. But for now, we just enter the address.
Yeah.
Then what happens?
Then you simply click the Deploy button. MetaMask will pop up asking you to authorize the transaction.
Right.
Double check you're deploying to Arbitrum Sepolia. Once the transaction is confirmed and goes through, the address of your newly deployed contract will appear in the deployed contracts list in Remix.
And save that address, I assume.
Absolutely. The guide emphasizes saving this address, as we'll need it in the next steps.
Upkeep contract deployed and address safely stored. Now we move on to deploying what's called the emitter contract. What's its job in this whole setup?
So the emitter contract is what generates the specific signals, the logs that will trigger our upkeep contract to go and fetch the data.
Like the starting gun.
Yeah, exactly. Think of it as the starting gun for the data retrieval race.
So in a real-world decentralized application, what kind of event might play this role?
Great question. The documentation gives a perfect example. It could be when a user makes a trade on a decentralized exchange or, performs some other action within your application that needs current, accurate data.
Okay.
For this Getting Started guide, they use a very simple contract called logemitter.sol purely for testing, so we can clearly see the triggering mechanism without other complexities.
Makes sense. Keep it straightforward for the demonstration. So how do we get this logemitter.sol contract deployed in Remix?
It's a pretty similar process, actually. First, you open the logemitter.sol file in Remix. The guide specifically mentions that you need to compile it using the 0.8.19 version of the Solidity compiler.
Oh, specific version. Okay.
Yeah, so make sure that version is selected in the Solidity compiler tab before you hit compile logemitter.sol.
Compiler version set, MetaMask still on Arbitrum Sepolia, environment still injected provider MetaMask?
Yeah.
What's next?
Then, just like before, you click the Deploy button on the Deploy and Run Transactions tab. MetaMask will again ask for confirmation. Always good to double-check the network.
Right.
Once the transaction is confirmed, the deployed emitter contract's address will appear. And yes, you guessed it, we need to save this address as well.
Addresses for both saved. Now we have our upkeep contract and our emitter contract out there on the test network. What's the next piece of the puzzle? It involves registering the upkeep right.
That's absolutely right. Now we need to tell Chainlink Automation, hey, listen for the specific logs from this emitter contract, and when you see them, trigger this upkeep contract.
Okay.
And this is done by registering a log trigger upkeep using the Chainlink Automation user interface.
Okay, so we navigate over to the Chainlink Automation UI for Arbitrum Sepolia and connect our browser wallet. What do we do from there to register this log trigger?
You'll click on Register New Upkeep and then select Log Trigger as the upkeep type. The UI will then guide you through the setup.
Right.
The first thing it will ask for is the address of the upkeep contract that you saved earlier. This is the contract to automate.
Okay, paste that in.
The documentation mentions you might see a warning about automation-compatible contract verification, but we can ignore that for this particular example.
All right, upkeep contract address entered. What information does it need next for registration?
Next, you provide the address of the emitter contract that you also saved. This is how Chainlink Automation knows which contracts to monitor for those trigger logs.
Gotcha.
After that, the UI might ask for the application binary interface or ABI of your upkeep contract if it couldn't automatically figure it out.
And we can get that from Remix.
Yeah, exactly. You can easily find the ABI in Remix by going to the Solidity compiler tab and using the button at the bottom to copy it.
ABI copied, if needed. Now, what's the specific log event we're telling it to watch out for?
The guide specifies selecting the log event from the emitted log dropdown. There's also an option for log index topic filters, which are optional and allow you to be very specific. But for this introductory example, we're leaving that field blank, meaning any log event from our emitter contract will do the trick.
So any log event from our emitter contract will set things in motion.
Yeah.
Almost there, right? What else do we need to configure during this registration process?
Just a couple more things. You'll need to give your upkeep a descriptive name, something that will help you track it in the UI.
Makes sense.
And importantly, you need to set a starting balance for the upkeep. The guide recommends setting it to one testnet link A for this example, noting that any unused link can be retrieved later.
One link, okay.
The check data field and other advanced options can be left blank for now. Finally, you click Register Upkeep, and MetaMask will pop up for confirmation. Once that's done, your upkeep is registered.
Upkeep registered. Now, we touched on this earlier, but let's make it crystal clear. The next step is funding the upkeep contract with testnet link. Remind us again why this step is crucial in this specific scenario.
Right. So in this particular design, the upkeep contract itself is responsible for covering the costs associated with verifying the data it retrieves from the data streams on the blockchain.
The on-chain part.
Exactly. This is separate from the broader Chainlink automation subscription. So, to enable our upkeep contract to pay for this on-chain verification, we need to send it some LNK tokens.
And the guide specifies sending one testnet LNK on Arbitrum Sepolia to the upkeep contract address we saved. Simple enough. funds sent. Now, how do we actually kick things off? How do we initiate the process of getting that price data? This is where our emitter contract comes back into the picture, right?
Precisely. The emitter contract has a function built into it that, when called, will generate a log. And this log emission is exactly what we've told Chainlink Automation to watch for.
Okay.
It's the trigger for the upkeep we just registered.
And how do we call that function in Remix?
So back in the Remix IDE, on the Deploy and Run Transactions tab, find your deployed emitter contract listed under Deployed Contracts and expand its details.
Yep.
You should see a button labeled Emit Log. Click that button.
Click Emit Log.
MetaMask will pop up asking you to confirm the transaction. Once you confirm and the transaction is processed, the log will be emitted onto Arbitrum Sepolia.
Okay.
The guide mentions that you can then go to the Chainlink Automation UI and find the corresponding upkeep transaction hash to monitor its status and confirm it was triggered.
Log emitted, upkeep triggered. Now, for the moment of truth. How do we actually see the Ethos price that was retrieved and stored by our upkeep contract?
Good question. The guide tells us that the retrieved and processed price is stored in a specific storage variable within our upkeep contract called last decoded price.
Last decoded price. And how do we go about accessing that variable in Remix?
On the Deploy and Run Transactions tab, locate your deployed upkeep contract this time and expand its details.
Okay, the upkeep contract.
You'll see a list of functions, including what are known as getter functions. These let you read the contract's state. Look for the function named last decoded price and click on it.
Click last decoded price.
The output that appears below will show you the stored price. Now, there's a really important point here about how this price is represented.
Ah, yes. The guide mentions that the Ethos stream uses 18 decimal places. So an output like 204,841,200,000,000 doesn't mean a price of $248 quadrillion.
Exactly. That would be nice, but no. It actually translates to a price of 2,484.121. That's a lot of implied zeros.
It really is.
And it's crucial to keep in mind that different data streams might use a different number of decimal places. The guide once again directs us to the Data Streams Crypto Streams page for specifics.
Right.
So when you're working with different data streams, always check their documentation to understand how to interpret the numerical values correctly.
Decimal places.
Right.
Seemingly small detail with a huge impact. Okay, so we've successfully seen the price. Now let's dig a little deeper into the code of the streams upkeep.losall contract itself. What are some of the key architectural concepts at play here?
Sure. The documentation highlights that the example code demonstrates all the essential interfaces and functions that an upkeep contract needs to interact with data streams via automation. It follows a similar pattern to more complex flows, but, like we saw, uses our simple log emitter as the trigger instead of, say, a DAX interaction.
And the guide mentions this interesting streams lookup revert within the checklog function. Why intentionally cause a revert? That seems odd.
Yeah, it might seem counterintuitive at first, but it's actually a really clever and efficient way for the contract to tell the Chainlink automation infrastructure which specific data streams it wants data from.
How does that work?
By reverting with a custom error called streams lookup and embedding the stream IDs within that error, the contract signals its data needs off-chain without burning gas on storage or computation on-chain.
Off-chain signaling.
Exactly. The guide points to EIP 3668 if you want the deep technical background. It's a really elegant design pattern.
Interesting. Using revert not just for errors, but as a communication tool. What happens after this checklog function executes and does its revert signal?
Right. So if the streams lookup is successful off-chain, meaning automation correctly identifies the requested streams, it will then call the check callback function in our upkeep contract, passing along the fetch data.
Okay.
In this example, check callback is pretty simple. It just returns true, basically saying, yep, proceed with the upkeep along with the fetch data. This data then gets passed on to the really crucial perform upkeep function.
And check callback runs off-chain too.
Yes, that's important. It's simulated off-chain by automation to decide if the actual perform upkeep transaction needs to be executed on-chain, saving gas if conditions aren't met.
Got it. And perform upkeep is where the real on-chain action happens, right?
Precisely. Perform upkeep runs on the blockchain when triggered. Its main job is to first decode the perform data that automation passes to it. This contains the signed data reports from Chainlink's Oracle network.
The actual price data.
Well, the signed report containing the price data. Then, perform upkeep extracts the report version. The guide mentions it currently supports v3 and v4 schemas. It's absolutely critical to validate this version.
Why is that so critical?
because the contract needs to know how to interpret the data structure. If it gets a version it doesn't understand, it has to stop, so it reverts with an invalid report version error.
Okay, so it checks the format first. What happens once the report version is validated?
Once it confirms the version, Perform Upkeep interacts with two other important contracts, the iVerifier proxy and the iFee manager.
We saw the verifier proxy address earlier.
Right. It first gets the fee required for verification from the fee manager. Then it authorizes payment of that fee using the LINK we sent it earlier. After handling the payment setup, it calls the verify function on the verifier proxy.
And that's the verification step.
That's the core on-chain verification. It's computationally heavy, but it's what cryptographically proves the data's authenticity and integrity on the blockchain. Think of the verifier proxy as like a trusted notary for the data.
Okay, a data notary. That makes sense. It saves our contract from doing that heavy lifting itself.
Exactly. It saves gas and complexity in our upkeep contract.
On-chain verification, the cornerstone of trustless data. And what happens after the verification is successful?
The verify function, if successful, returns the verified data report. Perform Upkeep then decodes this verified report into the right structure, like report v3 or report v4.
Based on the version it checked earlier.
Correct. Finally, it extracts the actual price from this decoded report and stores it in our last decoded price variable, and then it's available for us to query.
So that's the complete end-to-end flow within the upkeep contract, from receiving the perform data all the way to storing the verified price. Now, we mentioned earlier that the verifier proxy address is something we configure during deployment. What are its key functions again?
Right. The guide highlights that the iVerifier proxy interface exposes two main functions our contract uses. First, there's fee manager, which just returns the address of the fee manager contract needed to figure out the cost. And second, most importantly, there's the verify function itself. That's the one that takes the unverified report, the fee info, does the on-chain check, and returns the verified report data if it all checks out.
Okay, let's take a step back again and summarize the entire sequence just to lock it in. From emitting the log all the way to seeing the price.
Sure thing. So it starts when our log emitter emits a log.
Right.
Chainlink Automation detects this off-chain and triggers our upkeep. The upkeep's check log runs. Does the streams lookup revert to signal which stream it wants? Automation retrieves the signed report off-chain. Then check callback is evaluated off-chain. If it says go, the data is passed to Perform Upkeep, which executes on-chain.
Okay, now we're on-chain.
Inside Perform Upkeep, the report is verified using the verifier contract paying the LNNK fee. If verification succeeds, the price is extracted from the verified report and stored in last decoded price.
And then we query last decoded price in Remix.
Exactly. And then we can view that stored price using the getter function in Remix.
Ah.
That's the whole flow.
That's a fantastic overview. Really ties all the pieces together. Now, the documentation also touches on something about different ways feed IDs are represented. It mentions string in streams lookup, but bytes 32 in the decoded reports. Why the difference?
Yeah, that's a practical point. The streams lookup revert mechanism uses an array of strings because it's embedding info into an error message, which is text-based.
Okay.
But inside the actual data reports, for efficiency on-chain, feed IDs are represented as bytes 32, a fixed-size byte array, which is more compact and gas efficient.
Ah, gas efficiency.
Right. So if your contract logic needed to double-check that the feed ID you requested matches the one you received in the report, you'd need to convert between that string from the revert and the bytes 32 from the report.
Okay, so utilities exist for that conversion.
Oh yeah, standard Solidity libraries handle that kind of conversion.
Yeah.
Good to be aware of if you're building something more complex.
Got it. And lastly, the guide briefly mentions an optional function called check error handler. What's that for?
The check error handler is basically an optional safety net. It's a callback function that automation can call off-chain if it runs into trouble fetching the data after the streams lookup.
So if the lookup worked, but getting the data failed.
Exactly. It lets your contract define custom logic for handling those kinds of failures. In the example code, it's set to always return true for upkeep needed, meaning it triggers Perform Upkeep anyway, even if the report fetch failed. But you could change that. You can make it log the error or try a different stream or just decide not to perform the upkeep based on the error. It adds resilience.
Interesting. Safety net for potential hiccups. Well, that brings us pretty much to the conclusion of our deep dive into this Getting Started guide for Chainlink Data Streams.
Yeah, we've really walked through the key steps: deploying the upkeep and emitter, registering the upkeep with automation via a log trigger, funding it with LNNK.
Right, then emitting the log to kick things off, viewing the price, and even getting into the weeds a bit on the contract code like streams lookup and perform upkeep.
And understanding the role of the verifier. It covers a lot of ground.
And as the documentation suggests for your what's next exploration, you, our listener, are now hopefully equipped to go find lists of available stream IDs, understand the data schemas, and learn more about log trigger upkeeps.
Absolutely. This example truly provides a solid, practical foundation for understanding how to bring reliable, real-world data onto the blockchain automatically using these Chainlink tools.
So the final thought I want to leave you with is this. With this capability to seamlessly integrate verifiable real-world data right into smart contracts,
Sure.
what entirely new and innovative decentralized applications become possible?
Yeah, what kinds of on-chain systems that were previously stuck because they couldn't trust external info can now actually be built?
It's definitely a fascinating landscape to consider. Until our next deep dive.